Okay, so today we are actually going to learn how to calculate entropy. Yesterday we spent a lot of time learning what entropy was, so today let's figure out how to do a calculation with it. So first of all, what is entropy again? Entropy is a quantitative. What's quantitative mean?
Amount.
It's a specific numbered amount, right? So if I say 10 grams, I have a quantitative amount. So entropy is a quantitative measurement of disorder of a system. Okay. Again, the symbol for entropy we talked about yesterday is delta S, which means change in entropy, because that triangle means change in, right? Our units, there's actually two possible units for entropy. We can say joules per Kelvin, or we can also say joules per Kelvin times moles. So it all depends on what context. Honestly, it's the same thing. It really doesn't matter which one you choose. Okay, when we're talking about standard entropy, just like when we talked about standard enthalpy, we put that little circle after the S, and that means standard conditions. Okay, does anybody remember what the standard conditions are? 1 atmosphere, which is the same as 101.3 kPa. I want you guys to write that down. There are 3 different units for pressure. We have atmospheres, we have millimeters per mercury, and we have kilopascals. Sometimes we need to use kilopascals. That's why I gave you the value, just because you guys don't have that memorized. You have 1 atmosphere memorized. That's easy to remember. This one's a little bit more difficult. Okay, so for instance, do it. 1 atmosphere is 101.3 kilopascals. Okay, so for instance, a perfect crystal of whatever we're talking about at 0 degrees Kelvin would have an entropy of 0. So let's talk about what is 0 Kelvin.
Absolute zero.
It's absolute 0, which means all motion should be stopped. We should have 0 motion. If we have 0 motion, do we have any entropy? No. So does this actually exist? No, not yet. Anyhow, we haven't found anything that has 0 Kelvin. But for right now, it's just an idea. So to find our entropy under standard conditions, we do the same thing as we did for enthalpy. We take the summation of our products and we subtract it by the summation of our reactants. Again, we have to be under standard conditions. Actually, your homework over the weekend, we're actually going to be finding Gibbs free energy not under standard conditions. So you're getting ahead of yourself a little bit. Yes?
So is the entropy, is there more disorder the hydrogen element with more solids or liquid?
Yes. Yes, that's what we talked about yesterday. As you change states of matter, it gets more and more disordered. So gases are more disordered than liquids, and liquids are more disordered than solids.
So to get a gas to a liquid, that's where you think there's.
Yes. Well, and then yesterday we talked about a lot about sometimes things are spontaneous depending on what temperature under. Ice melts spontaneously as long as we're above freezing, right? But if we're below freezing, is it going to melt? No, so there's lots of factors that go into play when we're talking about entropy. So it doesn't always move towards disorder. We have to also take into account pressure and temperature. All right, so let's look at this example. We are going to calculate the amount of entropy in this reaction. So we already have our appendix open, so you guys can look up some values. So we're going to do the same thing we did for enthalpy. We're going to take the entropy of our products, add them together, subtract them by the entropy of our reactants, and we're going to get an answer, right? So somebody look up the entropy for hydrogen gas. 130.6. Somebody look up the entropy for chlorine gas. 223.0. And somebody look up the entropy for hydrogen chloride gas. 186. And that's for the gas, right?
Yep. Oh, wait.
It is.
Yeah, that's gas.
That's gas. Okay. Now, also do not forget about our little coefficient right here. That's going to go into play when we are doing our math, correct? So in order to find our change in entropy, again, under standard conditions, that's the only time this actually works, we have to take the summation of our products. Well, there's only one product, so that's pretty easy math, right? There's two of them, though, so we're going to take 2 times 186.79. Wow, I write like a kindergartner sometimes. 9. And we are going to subtract that by all of our reactants, which there's 2 of them, and of course I'm running out of room, so I'm going to go down a little bit. So we have 1 mole of hydrogen, so that's going to be 130.6. And we're going to add that to our 1 mole of chlorine, which is 223.0. Okay, and then all we have to do is plug this into the calculator, right? So, significant figures, what do? We don't really have to worry about significant figures right now. Why? Nothing was given to you in the problem, and these are all constants found in the back of the book, and constants don't affect significant figures. So honestly, keep a couple of numbers, call it good, right? So when I put this in the calculator, I got a positive 19.8, and then my unit is joules per Kelvin, and then if you want to, you can throw in mole. Same thing as enthalpy, right? Not any more difficult. We've already done this. Okay, so
it doesn't matter if you write joules over. Does it matter which one we write?
no, I do not prefer one over the other. Okay. Yeah, it's a typo. Sometimes when you make PowerPoints on a PC and then move them over to a Mac, it doesn't really. Okay.
What difference does it make to have the mole?
Well, that means 1 mole of. If I have. For this reaction, 1 mole is going to require that much increase in disorder. So if I have 2 moles, it would be double that. If I have 3 moles, it would be triple that. The more moles you have, the more increase of disorder you're going to have.
Yeah, but so if you didn't have the mole,
It's understood.
okay.
It's just so you can put it there or you don't have to. It's kind of understood that it's there. So, all right, moving on. All right, so the second problem that we're going to do is actually underneath that. It's right here. We are going to calculate the entropy for both the forward and the reverse reactions for the synthesis of water. So I'm actually going to put up my whiteboard so that we can have a little bit more room. Okay, so first of all, we need to write an equation for the synthesis of water. So what does synthesis mean? We're combining 2 things to form water. So what makes water? Hydrogen plus oxygen is going to yield H2O. And usually when we think of water, we think of the liquid form, right? Hydrogen is usually in the gas form, oxygen also in the gas form, right? So now we need to balance. So how do I balance this? 2 in front of water, and then we put a 2 in front of the hydrogen as well. Yay, everybody's balanced, right? Well, we just looked up the entropy for hydrogen gas, and that was 130.6. Somebody tell me the entropy for oxygen gas. 205. And then what about liquid water?
69.940.
All right, so whenever we are doing this, do not forget about our coefficients, right? Do not forget about them because we have to use those in our math, right? So now we need to find the entropy for this reaction, and then we're going to find our entropy for the reverse reaction, and we're going to see if something holds true that we already know. Okay, so let's go ahead and find the entropy. So we have to take the entropy of our products minus our reactants, correct? So we're going to take 2 times 69.94. We're going to subtract that by our reactants, which is 2 times 130.6 plus 205. Significant figures, anyone? So just keep a few, call it a day. So this is going to be negative 326.38. And your number might be a little bit different because the value I looked up for water was 69.91. So you might get just a little bit different answer than I got. And then again, it's going to be joules per Kelvin. I'll probably make you open it up in the test to look at these values. Alrighty, so part of the reaction. This is for the forward reaction, right? Mm-hmm. So now we need to do it for the reverse reaction. So the reverse reaction is no longer synthesis, it is decomposition. So let's try to find our entropy, understand our conditions for the reverse. So reverse, our products are going to be hydrogen and oxygen, right? So it's going to be 2 times 130.6 plus 205 minus 2 times 69.94. Anyone want to take a guess what you think the answer is going to be in the calculator? Positive 326.38 joules per Kelvin times 1. So, just like when we were doing enthalpy, what did we do when we reversed the reaction? We flipped the sign, right? We flip the reaction, you flip the sign. So do we have to solve for both the forward and the reverse? No. If you know the forward, you can figure out the reverse by flipping the sign. So easy enough, right? Alrighty, so alright, so now let's talk about free energy. And I kind of already talked about this a little bit yesterday. We started talking about Gibbs free energy. Gibbs free energy is talking about the amount of energy change in the system and is represented by delta G, right? Alright, so the Gibbs free energy is talking about the maximum amount of energy that can be coupled to another process to do useful work. So another process, we're in chemistry, what type of process do you think we're talking about? A reaction. So in chemistry, we're honestly talking about the maximum amount of energy to be added to a chemical reaction to do some sort of useful work, right? That's what we're talking about when we're talking about Gibbs free energy. We're talking about the energy involved in a chemical reaction. Okay. Gibbs free energy relates to two factors. Gibbs free energy is affected by both your entropy and your enthalpy. And so we get a nice, pretty equation. To find Gibbs free energy, you take your change in enthalpy and you subtract it by your temperature and your change in entropy. But again, we have to check our units here a little bit, right? Because sometimes things are in kilojoules, sometimes things are in joules. We have to make sure they match so that they cancel out. Temperature has to be in what? Kelvin. Temperature here has to be in Kelvin. Our entropy is talking about the change in entropy, and this is usually in joules per. I know. It's okay. Guys, it's okay. Okay, so entropy is joules per Kelvin. Does anybody know the unit for enthalpy? Enthalpy. Somebody look it up. It's probably on your enthalpy table right in front of you. Kelvin. Okay, so our kelvins are going to cancel out, right? Okay, the mole, just kind of like the mole with entropy, the mole with enthalpy is kind of understood, so it can stay there if you wanted to. It can cancel out if you wanted to. But basically, if our kelvins cancel out, we're going to be left with joules, which if you think back to physical science, isn't joules a unit for energy? Isn't delta G energy? So this makes sense a little bit, doesn't it? Yes. Uh-huh. Yeah, we can't do math with two different units. Okay. All right, so if delta G is negative, the process is going to be spontaneous. So if we do this math, if we take enthalpy minus temperature change minus our change in entropy, and we get a negative answer, it is telling me that it is going to be spontaneous. Okay, spontaneous reactions happen all by themselves. They don't need any energy, right? Our degree of disorder is going to be increasing, right? Okay, if delta G is positive, the process is not spontaneous. So if we do this work and we get a positive answer, it means that it's not spontaneous, so it is not going to happen all on its own. We're going to have to do something. We're going to have to change temperature, we're going to have to change pressure, we're going to have to add a catalyst, something, in order to get this reaction to happen, right? However, there's also a possibility for delta G to equal 0. And when delta G equals 0, the process is at equilibrium, which we really haven't talked about equilibrium a whole lot yet this year. And your homework over the weekend is going to talk about equilibrium just a little bit more. But equilibrium means that the reaction is happening in the forward direction as fast as it's happening in the reverse reaction. So nothing really looks like it's happening because your product is being formed as fast as it's being broken back down. So it's like, honestly, nothing's happening. But stuff is happening. It's just a constant cycle of product being formed, product being broken down. Example off the top of my head, I don't have one. So, I mean, when you take salt and dissolve it in water, it's at equilibrium. The salt is being dissolved as fast as it's being solidified, which is being dissolved, which is being solidified. It's just happening over and over and over and over again so fast, but you can't see it. So, okay, so let's do a nice, pretty, hard one. Okay, so calculate the free energy for the following reaction to determine if it is spontaneous at 25 degrees Celsius. Before we even start this process, 25 degrees Celsius,
That's not.
We need what kind of degrees? We need Kelvin. We don't want degrees Celsius. So automatically we have to add 273 to this, which you might as well just get used to this. This is going to be 298 Kelvin. 25 degrees Celsius is a standard temperature. So 298 Kelvin, 25 degrees Celsius, same thing. Okay. All right, so we need to find the free energy. Free energy is delta G equals enthalpy minus temperature times entropy. But did they give us enthalpy? Did they give us entropy? So what do you think we're going to have to do first? We're going to have to solve for them, right? Because we want delta H and delta S, not H and S, right? So I looked them up for you. Okay, so I used the book to come up with our values for our enthalpy and our entropy. Enthalpy is really, really easy for us to do. Why is enthalpy really easy for us to do this calculation for? Because we have carbon solid, that's elemental, right? The enthalpy of a thing elemental form is 0 because there is no formation, it's already formed, right? Same thing for oxygen gas, it's elemental. So we didn't form it, it was already created, right? So 0, 0. So our change in enthalpy is already done for us, correct? So we don't have to do that math. We can just plug that part into the equation. However, we do have to do the math for our entropy, right? So to find our change in entropy, we have to take our products, which is 214, and we're going to subtract it. No coefficients, so we don't have to worry about adding any coefficients, right? Subtract it by 5.69 plus 205. So our entropy is going to be positive 3.31 joules per Kelvin. Does anyone see a problem when we're going to use our free energy equation in just a second by our enthalpy and our entropy issue? Anyone? Ones in kilojoules, ones in joules. So you guys just need to get in the habit, whenever you see kilojoules, just automatically convert it to joules. And that way you won't accidentally make a mistake. So now that we know what our entropy is, we can now solve for Gibbs free energy, right? So Gibbs free energy, which is delta G, delta G is going to be equal to our change in enthalpy minus our temperature times our change in entropy. Our enthalpy is in kilojoules, so I'm just going to go ahead and convert it to joules. How do I do that? Multiply by 1,000, move the decimal how many times? 3, so negative 393,500 joules per mole. Actually, not going to put the units because I'll run out of room if I put the units. Okay, and we're going to subtract that by our temperature, which we found to be 298, right? Times our entropy, which we just found to be a positive 3.31. So if we put this in our calculator, we get negative 394,486. Significant figures, anyone? Yes. Why 2? We were given 25 degrees Celsius in the problem, so we actually have significant figures to pay attention to this time around. So how would I round this? Negative 3, 9, 1, 2, 3, 4. Or you could round it up to 40,000, but that is one significant figure, so that creates a whole other series of problems. So, or we could do negative 4.0 times 10 to the 4th. I mean, there's lots of different ways we can round this to make everything nice, pretty, and happy, right? Yes, and I ran out of room. Our unit here is going to be joules per mole, or just joules. Yeah, if you would have put negative 390 kilojoules, that would have been fine. Alrighty, so that concludes our notes today. So we have a little bit of homework.